Hi, welcome to Joe's Classroom and the lecture series on frequency domain analysis. In this lecture, we are going to understand the theory behind the Bode plot of systems with transfer functions having complex poles or zeros. Before going into the details of this topic, let us have a quick review of what we learned in the previous lectures. Especially in the previous two lectures, we understood the theory behind the Bode plot of systems with poles and zeros at origin and non-zero poles and zeros on the real axis. If you take the system with pole at origin, this is going to be the pole zero plot. And if the system has got this kind of pole zero plot, then the transfer function of the system is going to be of the structure g of s is equal to k by s power n, where n is the number of poles at the origin. There may be one pole or multiple poles. So depending upon the number of poles at origin, this n will vary. And if I have a 0 at the origin, then the expression is going to be, the transfer function expression is going to be like this. G of s is equal to k into s power n. And again, n is the number of zeros at the origin. If I have g of s is equal to k by s power n corresponding to the poles at origin, then the Bode magnitude plot and the phase plot are going to look like as given in this diagram. Magnitude plot is going to be a decreasing straight line with a slope of minus 20 n decibels per decade, and it will pass through 1 comma 20 log k. And the phase plot is going to be a horizontal straight line at minus 90 n degree. And if it is zeros at origin, then the transfer function, as said before, is g of s is equal to k into s power n, and the Bode magnitude plot is going to be a increasing straight line with a slope of plus 20 n decibels per decade, and this line also will pass through 1 comma 20 log k, whereas the phase plot is going to be a horizontal straight line at 90 n degrees. And if I have the poles at the real axis, on the real axis, okay, then this is going to result in first order terms in the transfer function. Since this is a pole, the first order terms will be lying on the denominator of the transfer function, and the transfer function will have this structure k by 1 plus ts the whole power n. In this case, the pole is going to be minus 1 by t. For such transfer functions, the Bode magnitude plot will have two straight lines. One straight line with 0 decibels per decade. I'm talking about the asymptotic Bode plot, not exact Bode plot. The asymptotic Bode plot will have two lines, one with 0 decibels per decade, and this will be valid up to the corner frequency. Corner frequency is given by 1 by t. And beyond the corner frequency, the slope of the line is going to be minus 20 n decibels per decade. And similarly, the phase plot is going to be a nonlinear curve starting from 0 and reaching minus 90 n degrees as omega increases from 0 to infinity. And if the system has got zeros at the real axis, then the same term is going to appear in the numerator. In that case, everything what I explained for poles is valid, except that the second part of the line, I mean the line beyond this corner frequency, is going to be an increasing straight line with plus 20 n decibels per decade, and the phase plot will vary from 0 to plus 90 n degrees as omega increases from 0 to infinity. So we have seen systems with poles either at the origin or the real axis, or zeros at the origin and the real axis. Now, the last possibility of the poles lying on the complex plane is, as complex poles or zeros. Complex poles. This is what we are going to, focus in this lecture. So that is the systems with transfer functions having complex poles or zeros. So far, in all the pole zero plots which I have shown to you, I have marked the poles and zeros on the left side of the complex plane, left of plane, LHP. Okay, so the systems having all their zeros and poles on the left side of the complex plane is what we are going to call it as the minimum phase systems. And all the discussions we had in lectures corresponding to this Bode plot, and even this lecture now is going to deal only the minimum phase systems. That means these discussions may not be valid for non-minimum phase systems which have got their zeros or poles on the right of the S plane. Those systems, that is the non-minimum phase systems, will be dealt in a separate video. As far as the systems with complex roots are concerned, one important thing the viewer has to understand is the complex roots for an LTI system are going to occur in conjugates. This is because the LTI systems will result in differential equations with real coefficients. In mathematics, you might have studied that all polynomials having real coefficients in their equation will result either in real roots, or if at all there are complex roots, they will occur in conjugates. Since we are also going to have differential equations with real coefficients in it for LTI systems, we also will have the complex roots as conjugates. This is an important point to note. Therefore, if the complex roots are going to occur as conjugates, then these roots, I mean the pair of roots, are going to result in second order polynomial. Therefore, the systems with complex roots will result in quadratic polynomials in their transfer function. When I say the quadratic polynomial, this is going to be the structure. If the quadratic polynomial is going to appear at the denominator, the roots are actually poles. And if the quadratic polynomial is going to occur in the numerator, that is going to result in zeros. So when I say the systems with complex poles or zeros, therefore it means that the systems having the transfer function with quadratic polynomial terms either in the denominator or in the numerator. First, let us take a system with complex poles, I mean the second order polynomial in the denominator. In that case, this is going to be the general structure of the transfer function, where k is a real constant and n is an integer. Let us evaluate the roots of this equation. Let us just examine the roots of the equation. So we should know, whether the roots are going to be really complex conjugates. So if this is going to be the characteristic equation for one of the term, then S is going to be, if you can apply minus of b plus or minus root of b square minus 4ac by 2a, then the roots of this characteristic equation will be minus theta omega n plus or minus j omega n into root of 1 minus theta square. So by observing this, you will be able to understand that as long as the theta value is lesser than 1, as long as the theta value is lesser than 1, the roots are going to be complex conjugates. Therefore, for a quadratic polynomial to have complex conjugate roots, the important condition is the damping ratio or the theta should be lesser than 1. And this is an important point to note. In the previous discussions, we understood that the transfer function has to be expressed in time constant form. To express this transfer function in time constant form, this constant term should be 1. So if I want to make this as 1, this omega n square have to be taken out of this term, this entire term. Okay, so when I take this omega n square, you have to be a bit careful because it is having a multiplicity of n, and therefore when I take this out, it has to be omega n square the whole power n. If I take that out, omega n square the whole power n, this is going to be, the term inside the brackets. So this will have 1 by omega n square, and this will also will have 1 by omega n square, and here already omega n is there, and it will get cancelled. Only one omega n will remain in the denominator, and this entire term becomes 2 zeta 1 by omega n, and this is going to be a constant. And omega n being a constant, omega n will have a specific value. So therefore, this term I can combine with this k, and let me call the k by omega n square the whole power n. Yeah, the whole power n is missing here. That's a mistake. So it should be omega n square the whole power n. So let me call this entire term as k, capital K. Okay, so therefore the same expression can be rewritten in this form. And let me make another substitution also here. Let me substitute 1 by n is equal to t. In our previous lecture on systems with non-zero real poles, you might have noticed that the inverse of the corner frequency, we made it as t. Here also, in another few minutes, in this lecture itself, we'll be able to see that in the case of systems with complex poles or systems with quadratic terms in their transfer function, the natural frequency of oscillation omega n is going to take the role of the corner frequency. That we will be able to see in another few minutes. So therefore, there is nothing wrong in taking 1 by omega n as t. So with this substitution, okay, so I can make this as 1 by omega n the whole square, and therefore this term I can write it as t square s square, and 2 zeta ts plus 1. Writing this transfer function, the second order transfer function, in this form is what we call it as the time constant form. This is, we call it as the pole zero form. Please note, in pole zero form, our x square term will have a coefficient of 1, whereas in time constant form, the constant should be 1. The constant term should be 1. That is how, you can distinguish the pole zero form and the time constant form. So when it comes to the Bode plot or any frequency domain analysis for that matter, we represent the systems in time constant form. So let us take the transfer function in the time constant form now, and to plot the Bode plot, you need to know g of j omega. So g of j omega is obtained by just replacing s by j omega, and this j omega the whole square will result in minus omega square, and s will result in j omega, this is 1. Okay, and if you look at these terms, this has become a real term, and there is one more real term here. We will combine them together, 1 minus t square omega square, and this is the complex term. So to sketch the Bode plot, we need to separate the magnitude and phase. Let us take the magnitude first. For any complex number of the form a plus jb, the magnitude is given by root of a square plus b square, and here the a or the real part is 1 minus t square omega square the whole square plus this term square, that will result in 4 zeta square t square omega square. So square root of this a square plus b square term and whole power n is there. Of course, we need to convert the magnitude to decibels. So if I have to do this, this is what I will get. And this is of the form log of a by b, and log of a by b is given by log a minus log b. If I apply this, this is what I will be getting. So log of 20 log of this minus 20 log of this entire term, and here I have combined this the whole power 1 by 2, the square root 1 by 2 and n as n by 2. And of course this n by 2 can be brought to here, and in that case it is going to be minus 10n. So this is the expression which exactly represents how the magnitude varies with respect to omega. Of course, it is a nonlinear function of omega. Okay, so this is the final expression. Now let us focus on the angle of g of j omega. Of course, this can be written in this way. And in this case, I need to find out this angle of this number, complex number, and I can multiply it with n. Okay, so let me find out the angle of this. The angle of this is going to be, angle of 1 minus angle of this. Angle of 1 is 0, and angle of this complex number I can obtain by tan inverse of b by a. B is 2 zeta t omega, and a is this together, 1 minus t square omega square. So I got it as tan inverse of 2 zeta t omega divided by 1 minus t square omega square. Of course, to get the angle of this entire complex number, that is the the whole power n, I have to multiply by n, and if I do that, I will get minus n times tan inverse of 2 zeta t omega divided by 1 minus t square omega square. So for this transfer function, which is written in time constant form, the corresponding magnitude expression is this, and the angle expression is this. So with these two expressions, I can, sketch the exact magnitude plot and the phase plot. However, now let us examine whether I can approximate these expressions to get a simplified magnitude plots. Here, rather than taking a specific example to understand the shape and all, I'm just straight away going into understand whether this expression will have any asymptotes, whether I can approximate this expression by some asymptotes analytically. So let me take that expression here, okay, and let me take a first case where the frequency is far lesser than 1 by t. Of course, we know that 1 by t is equal to omega n. That is the corner frequency. For all frequencies lesser than the corner frequency, of course, t square omega square is far lesser than 1. So, I have given a few examples here, and you can just verify with their numerical results. If that is so, then t square omega square becomes negligible compared to 1. If t square omega square is negligible, of course, zeta square t square omega square is also negligible. Because this is a very small number, anyhow, the zeta is going to be a number between 0 and 1. So therefore, zeta square is going to be still lesser, and therefore, this entire term 4 zeta square t square omega square is also going to be negligible. In such case, this entire term is reduced to 1. So when compared to 1, all these terms become very negligible, and the resulting term is 1. Log 1 is 0, and therefore this entire term vanishes, and the only term remaining in the expression is 20 log k. Obviously, this is a straight line with 0 decibels per decade and having a magnitude of 20 log k. So therefore, what we understand is for all frequencies lesser than omega n or the corner frequency, I can assume the Bode plot to be a straight line with a magnitude of 20 log k and slope 0 decibels per decade. And this makes me understand that up to the corner frequency or up to 1 by t, the contribution by this entire denominator term is negligible and it is neglected. And this 20 log k is contributed only by this constant k term. If this is the case for frequencies lesser than the corner frequency, let us see what is going to be the case for frequencies greater than the corner frequency. In such case, t square omega square becomes more prominent when compared to 1, and that you can verify from these examples also. In such case, this term 1 minus t square omega square, I can, in this is 1 is going to be negligible when compared to this, and the whole term square is going to be t power 4 omega power 4. And when you compare these two terms, so now this entire term is t power 4 omega power 4. Because of this theta square, this term is going to be smaller when compared to t power 4 omega square, omega power 4. Therefore, in such case, I can omit this term also. Therefore, whether it is a frequency greater than the corner frequency or lesser than the corner frequency, the contribution by this term is always negligible. Okay. So therefore, for approximations, we can always omit this term. So therefore, this entire term becomes t power 4 omega power 4. So let me, write taking only that term here, and this is, t omega, the whole power 4 I can write. So this 4 I can bring it to here. So this is going to be the expression, expression of the straight line approximation or the expression of the asymptote beyond this corner frequency. So what is going to be the slope of this? Of course, this is a straight line, okay? And by looking at this equation of the straight line itself, you should be able to say that slope of this line is going to be, minus 40n. So if you still have doubt, you can take two frequencies at 1 decade apart, at one frequency at 1 by t and another frequency at 10 times 1 by t, and calculate this, the gain in decibels. You'll be able to see that, the difference is only minus 40n. That means as the frequency increases 10 times or the frequency moves by 1 decade, the change in the magnitude is minus 40n decibels per decade. So the slope of the line beyond this frequency is minus 40n decibels per decade. Having understood this, let us work out an example. This is the transfer function given. Obviously, looking at this transfer function, we understand that this is in time constant form because the constant is 1. So I can always, equate this or compare with this general expression of k by t square s square plus 2 zeta ts plus 1 the whole power n. And if I do the comparison, then I find that k is equal to 1 and n is equal to 1. And t square is going to be 0.01 which means that t is equal to 0.1 and 2 zeta t is equal to 0.1. From that I can get zeta as 0.5. Obviously, zeta is between 0 and 1, and therefore this is going to result in complex poles that we have to ensure at the beginning itself. If the zeta is going to be 1 or greater than 1, it means that this is not going to result in complex pole, but it is going to result in two real poles. In that case, you have to factorize this polynomial and consider this as with systems having non-zero real poles, which were dealt in the previous lecture. That is a very, very important point to note. And here already the transfer function is given in time constant form. Sometimes the same transfer function can be given in pole zero form also. In that case, the denominator will be of this form. In this case, this is in the form of s square plus 2 zeta omega n s plus omega n square. If the transfer function is given in this form, I mean with the coefficient of 1 for s square term, then from this how you can find omega n is, this if you compare omega n square is equal to 100 and therefore omega n is equal to 10, and this term is 2 zeta omega n, that's equal to 10, and you can get zeta as 0.5. In either way, you can find out the zeta value and decide whether this is the quadratic term with complex poles or the real poles. They are going to result in complex poles only if the zeta value is between 0 and 1. Anyhow, we have understood the omega n value, we have got the omega n value or t value. Then immediately we can find out the corner frequency. Corner frequency is given by 1 by t, and it is equal to 1 by 0.1. It is equal to 10 radians per second. And of course, you can mark this corner frequency in the semi-log graph. Once it is done, it is a matter of finding two straight lines, drawing two straight lines. One straight line, up to this corner frequency, and another straight line beyond this corner frequency. Up to this corner frequency, it is going to be a horizontal straight line with a magnitude of, 20 log k. 20 log k here is 20 log 1, which is going to be 0 decibels. So it is going to result in a straight line at 0 decibels. And beyond 1 by t, or beyond the corner frequency, it is going to have a minus 40 n decibels per decade. Here n is equal to 1, and therefore the slope is going to be minus 40 decibels per decade. And of course, this has to pass through 1 by t, 20 log k, and this is the straight line. Okay, so you got two asymptotes drawn here with the help of these facts. Once that is done, once you draw the Bode magnitude plot, that is asymptotic magnitude plot, you can find the phase plot. Usually the phase plot is drawn as an exact plot using this expression. So substituting the value of n, zeta and t, you will get this expression. Of course, this expression can be computed for different values of omega, and you can get those points, connect those points, and you get the phase plot. So it is necessary to take more points, at least 2 points in a decade, so that you get a smoother curve. And the important point you have to note in the case of a phase plot is this: from which angle it starts and to which angle it goes as the frequency increases from 0 to infinity. When omega tends to 0, that is when for smaller values of omega, Of course, this is going to be, 0. This is numerator is 0 and this is also 0. 0 by 1 is equal to 0 and tan inverse of 0 is equal to 0. And as omega tends to infinity, if you put infinity, you will get infinity by infinity, which is an indeterminate form. And then you can apply the, L'Hospital rule here. And if you apply this L'Hospital rule and apply these limits, you will get that, the angle as minus 180 degree. It means for a quadratic polynomial or quadratic term in the transfer function, especially when it is in the denominator as pole, the angle changes from 0 to 180 degree as the frequency increases from 0 to infinity. And at the corner frequency, it will be half of minus 180 and therefore it is going to be minus 90 degree. Now, as far as the magnitude plot is concerned, we have drawn only the asymptotic plot, but it is necessary how far this asymptotic plot is, uh, close to the exact plot. Let us try to do this. So, this is the expression representing the exact plot which we derived earlier, and specifically for this system with the given values of t and theta. Yeah, of course, this is a value, this is the expression, and obviously I can plot this. Okay, this is what you will get if you plot this expression over this frequency range. Let us compare this with the asymptotic plot. So there is not much difference. For frequencies far greater than the corner frequency and for frequencies far lesser than the uh, corner frequency, they almost exactly match. And we have to examine how it is going to behave at the corner frequency. If I zoom this is what you will be able to see. There is not much difference, but the difference may be higher also. It need not be so coinciding. There may be some error. And it will be interesting to note that this error is going to depend on the theta value. That is the damping ratio. To understand this a little more, I'm going to take you to another website which shows the relationship between the damping ratio and the error in an interactive manner. So this is the website. The corner frequency or the frequency of natural oscillation is entered as 10 radians per second, and the theta value I can vary from 0.05 to 0.99. This setting is given because this poles are going to be complex conjugates only for the theta ratio of 0 to 1. So initially the value is 0.05 and I can vary this theta value by sliding over the sliding bar. If you come to this plot, this black dotted line represents the exact plot and the colored line given in a light shade represents the asymptotic plot. The same is valid for the phase plot also. Now let us increase the theta value. Let us see what happens to the magnitude plot and the phase plot. See, the resonant peak of the system has come down. As I increase the theta value, you can observe that the resonant peak varies with respect to theta value. As resonant peak varies with the theta value, the error between the asymptotic plot and the exact plot also varies at the corner frequency. And when it comes to the phase plot, as the damping ratio becomes smaller and smaller, this, the change in the phase angle becomes steeper and steeper. And this is what we are able to understand regarding the variation of the uh, asymptotic plot from the exact plot. This can be well understood from this diagram also. This diagram represents the Bode magnitude plot zoomed near the corner frequency for various values of theta. So for smaller values of theta, the difference is too much. At the corner frequency, the maximum error will be 28 decibels. And as theta increases, for example, at theta is equal to 0.1, the maximum error is going to be plus 14 decibels. And as theta increases, the error also decreases. Please note that this dashed line represents the asymptotic plot. So when the value of theta is around 0.707, the difference or the error between the asymptotic plot and the phase plot is minus 3 decibels. And it goes on. Okay. And with the discussion so far, what are the takeaways? If my transfer function is going to be in this form, which is going to result in complex conjugate poles, then the asymptotic Bode magnitude plot is going to have a pair of straight lines. Okay, the pair of straight lines change their slope at the corner frequency, and the corner frequency is given by 1 by t, or it is equal to the natural frequency of oscillation. Up to the corner frequency, it is going to be a horizontal straight line with a magnitude of 20 log k, and beyond the corner frequency, it is going to be a straight line with minus 40 n decibels per decade. As far as phase plot is concerned, the phase varies from 0 degrees to minus n times 180 degrees as the frequency varies from 0 to infinity. So having understood the systems with complex poles, it is time to, understand the systems with complex zeros. For complex poles, these are the two expressions which represents the exact plot of the magnitude and the phase plot. And in the same way, if I take a similar system with complex zeros, then this term in the denominator goes to the numerator. And this is what is going to be the transfer function of such systems. So obviously we know that even from our previous experience, when the same term goes to the numerator, the expressions will remain same, only there will be a change in the signs. Obviously this negative sign will become positive, and this negative sign will also become positive. Anyhow, we are not going to derive this. The viewer can try deriving these expressions as we derived for the poles. And one important thing regarding the phase plot, in the case of systems with complex poles, it varied from 0 to minus 180 n, whereas in the case of systems with complex zeros, the phase is going to vary from 0 degree to plus 180 n degrees. When it comes to the asymptotic plot, for poles we understood this, we just now saw that. And what is going to be the difference? Up to the corner frequency, again it is 20 log k as before. Only thing is the slope of the line is going to change from minus 40 to plus 40 n decibels per decade. To understand this a little more, you can try this problem. I will leave this problem to the viewer, but still not the entire problem. I will just explain the preliminaries, and the rest of the thing you can try. Of course, this is a transfer function with a quadratic polynomial in the numerator, and only thing is we have to verify this will result in complex conjugate poles. How do I do that? If I keep the transfer function as it is, then I can compare it to s square plus 2 zeta omega n s plus omega n square. In that case, omega n square is equal to 25 and omega n is root of 25, that is equal to 5 radians per second. And this is 2 zeta omega n. If I equate that to 2 zeta omega n and substitute the value of omega n is equal to 5, I can find the zeta value as 0.2. This zeta equal to 0.2 is obviously lesser than 1, or it falls in the range of 0 to 1, and therefore this quadratic polynomial is going to result in complex conjugate zeros. So can I straight away go to sketching the Bode plot? No, you cannot. You have to convert this transfer function into time constant form first. How do you do that? You have to make this constant as 1. So to make this constant term as 1, you have to take this 25 outside. And if you take 25 out, so every term has to be divided by 25. So in that case, this constant becomes 20 into 25, that's 500. And this is what you get inside. Please note that if you take this transfer function as it is, it will be misleading because the k value you will be taking is 20, but it is not actually so. The k value is 500. You have to be a bit careful. So before plotting any, whether it is magnitude plot or phase plot, in frequency domain analysis, it is better to convert the transfer function into time constant form. Okay. Now, of course, we know that this is in the form t square s square plus 2 zeta t s plus 1. So therefore, this is t square, and I can get t as square root of 0.04, that is 0.2. And of course, this also, I can equate again if you want to 2 zeta t, and you can get zeta is equal to 0.2 again. Okay, so which confirms that this will have complex conjugates roots. Now, having transformed to time constant form, now you can use this expression to sketch the Bode plot. Of course, you have to plot the magnitude plot as well as the phase plot. Both the plots are given here, and you can see that this is going to be 20 log 500. This magnitude is going to be 20 log 500, and this slope is going to be plus 40 decibels per decade because it's in the numerator and its contribution is from zeros. And this phase plot will start from 0 and it will end at plus 180 degree. Try plotting it yourself. With this, we are winding up this lecture. And in the next lecture, we will see how we can sketch the Bode plot if in the given transfer function I have terms of all these kind. I've got terms with poles or zeros at origin, non-zero real poles or zeros, or complex conjugate real poles or zero. If I have a transfer function having a combination of all these terms, then how do I sketch the Bode plot? That is what is going to be the focus of next lecture. And I request you to leave the questions in the comment box so that I can help you by answering them. Thank you.